Hi, welcome to the WTAMU Virtual Math Lab. This video will step you through College Algebra Tutorial 23B Example 1. In this example, we want to solve the rational inequality x minus 1 over x plus 5 is greater than or equal to 0, write our answer in interval notation, and graph the solution set. In step 1, we want to write the rational inequality in standard form. This means we want to set the rational expression either greater than or less than 0. The reason we are doing this is 0 is our magic number. It is the only number that separates the negatives from the positives. If an expression is greater than 0, then there's no doubt that its sign is positive. Likewise, if it's less than 0, its sign is negative. We cannot say this about any other number. Since we are working with inequalities, this idea will come in handy. With this technique, we will be looking at the sign of a number to determine if it is a solution or not. This inequality is already in standard form. In step 2, we want to factor the numerator and denominator and find the values of our variables that make these factors equal to 0 to find the boundary points. The boundary points will mark off where the rational expression is equal to 0 or undefined, which is where the denominator is 0. This is like the crossover point since 0 is neither positive nor negative. Neither the numerator nor denominator can factor, so let's go ahead and set the factors we have in each of them equal to 0. Setting the numerator equal to 0, we get x minus 1 equals 0, and setting the denominator equal to 0, we get x plus 5 equal to 0. Doing the inverse operation of adding 1 to both sides, we get x minus 1 plus 1 equals 0 plus 1, which will simplify to be x equals 1. Doing the inverse operation of subtracting 5 from both sides, we get x plus 5 minus 5 equals 0 minus 5, which simplifies to be x equals negative 5. So it looks like we have two boundary points, negative 5 and 1. In step 3, we want to use the boundary points from step 2 to mark off test intervals on the number line and list all the factors found in step 2. Here we have marked off our boundary points of negative 5 and 1. Note that we are using an open hole at negative 5 because this is the value that causes the denominator to be 0, so we cannot include that value. But we will have a closed hole at x equal 1 since we need to include where this rational expression is equal to 0. Note that our boundary points mark off three sections on the graph: negative infinity to negative 5, negative 5 to 1, and 1 to infinity. In step 4, we need to find the sign of every factor in every interval. When we do this, we can choose any point in an interval to represent that interval. Once we choose this value, we will plug it into each factor and determine if the sign of that factor is either positive or negative. Let's go ahead and choose negative 6 from the first interval of negative infinity to negative 5 to plug into this. Plugging a negative 6 into the numerator's factor, we get a negative 6 minus 1 equals negative 7. Since we got a negative number, the sign of that factor in that interval is negative. Now let's plug negative 6 into our denominator's factor. This will give us negative 6 plus 5 equals negative 1. So it looks like we have another negative factor in that interval. Moving to the second interval of negative 5 to 1, let's go ahead and choose 0 to plug in. This will give us 0 minus 1 equals a negative 1 for that top factor, which means that factor is negative for that interval. Plugging 0 into the other factor, we get 0 plus 5 equals 5. So this factor is positive in that second interval. Let's check out that last interval of 1 to infinity. Let's choose 2 to plug into x minus 1 and get 2 minus 1 equals 1. Since 1 is a positive number, this factor is positive in that last interval. Plugging the 2 into x plus 5, we get 2 plus 5 equals 7, which means this factor is also positive in that last interval. In step 5, we want to use the signs found in step 4 and determine the sign of the overall rational function in each interval. In the first interval of negative infinity to negative 5, we would have a negative divided by a negative, so the sign of the quotient of those two factors is positive. In the second interval of negative 5 to 1, we would have a negative divided by a positive, so the sign of the quotient of those two factors is negative. In the third interval of 1 to infinity, we would have a positive divided by a positive, so the sign of that quotient of those two factors is positive. In step 6, we want to write the solution set in interval notation and graph it. Remember that the original inequality in standard form is x minus 1 over x plus 5 is greater than or equal to 0. To be greater than or equal to 0 means that the rational expression has to be positive or equal to 0. Looking at the bottom line, it looks like the two intervals that the rational expression is positive is the first one, negative infinity to negative 5, or the third one, which is 1 to infinity. Since we are including where this expression is equal to 0, we will have a boxed end at 1. But since negative 5 causes the denominator to be 0, we will have a curved end at negative 5. So our final answer for the interval notation is the open interval of negative infinity to negative 5 union with the closed interval of 1 to infinity. The graph will look like the interval notation. We will have a curved end at negative 5 and shade everything to the left of that, and a boxed end at 1 and shade everything to the right of that for our final answer for the graph.